At Jackass Flats in Nevada, liquid hydrogen entered a nuclear reactor, absorbed its heat, and escaped through a rocket nozzle fast enough to produce thrust. A 1968 photograph shows Phoebus 2A doing exactly that.
The firing happened on a test stand. So did every other firing in Rover and NERVA. NASA and the Atomic Energy Commission built reactors, engine systems, rail cars, control rooms, and acres of concrete around them. They proved that nuclear heat could propel a rocket on Earth. Nothing the program built ever reached space. NASA wanted the engine because missions beyond the moon were heavy, and chemical upper stages had to carry enormous quantities of propellant. Nuclear thermal propulsion promised roughly twice the specific impulse of comparable chemical stages. For the same propellant mass, that could mean more payload, a different trajectory, or more room for everything a distant mission needed. Project Rover began as reactor research in 1955. The joint NASA-AEC NERVA engine program followed in 1961. Across both efforts, 20 rocket reactors and 2 engine systems were ground tested in Nevada. Early machines damaged fuel and shook components apart. Later ones ran longer and hotter. The same campaign also left contaminated machinery, buildings, and ground. The operating cycle was direct. A turbopump forced cold liquid hydrogen through passages in the reactor. Fission heated the core. The hydrogen became extremely hot gas, expanded through the nozzle, and accelerated out the back. There was no chemical combustion chamber. Reactor temperature, fuel survival, hydrogen flow, and nozzle performance all had to cooperate inside one machine. This was steady reactor power, unlike nuclear pulse proposals that used repeated explosive charges. The propellant was hydrogen because a low molecular weight gas can leave a nozzle at very high velocity. That exhaust velocity produced the efficiency advantage. It also made the hardware difficult. Very cold hydrogen entered a core hot enough to damage its own fuel elements. KIWI addressed the basic question: could a reactor create useful rocket thrust at all? Tests in 1959 demonstrated the solid core process. Hydrogen passed through a hot reactor and exhausted through a nozzle. KIWI moved toward higher power and a more flight-oriented geometry. These were reactor test articles. The pumps, controls, shielding, and structure of a complete engine still lay ahead. Phoebus 2A operated at about 4,100 megawatts thermal, making it the most powerful nuclear rocket reactor ever operated. Its equivalent thrust was calculated at between about 210,000 and 250,000 pounds. The figure was derived from reactor performance because Phoebus 2A remained a reactor test article rather than a complete engine on a flight-rated thrust stand. Fuel survival came next. Early cores cracked, corroded, and vibrated. Protective coatings failed, and fission products escaped. KIWI's vibration and fuel element damage were eventually understood well enough for engineers to change element geometry, coatings, support structures, and operating procedures. The changes can be traced across the increasingly longer and hotter test series. The safety program included deliberate destruction. Phoebus 1A suffered severe core damage after inadequate cooling. KIWI TNT was different. Engineers intentionally destroyed a working reactor to collect data about a launch accident. The test was planned and instrumented. Its destruction made the boundary explicit. A damaged reactor could scatter fuel particles and fission products. Failures and destructive testing contaminated parts of the Nevada test area. Fuel development, nevertheless, made substantial progress. Pewee later reached hydrogen exhaust temperatures around 2,550 Kelvin, a key measure of nuclear thermal performance. The program had learned to operate experimental fuel at demanding temperatures on the ground. It had not established a production flight core with manufacturing controls, qualification margins, and a demonstrated service life. Then came endurance. NRX A6 completed a 62-minute run at full power. This was one continuous full-power test, rather than time accumulated across a collection of starts. That distinction matters because later engine system totals combined time from repeated starts and separate runs. That continuous run was a strong hour-scale endurance result under full-power ground test conditions. The XE experimental engine system then addressed throttling and restart. XE and XE prime accumulated roughly 115 minutes of operation across 28 starts. That was cumulative time, not a single burn, and the limited number of development articles could not establish flight reliability. It did show that the engine system could start, change operating point, shut down, and start again under test conditions. At Engine Test Stand 1, XE fired downward into a system that simulated altitude. The assembly combined the reactor with turbomachinery, controls, nozzle, and components derived from flight engine designs. This was the closest rover and NERVA came to an integrated engine NASA might fly. The test connected the reactor to the rest of an engine under controlled ground conditions. The test cells still supplied things a spacecraft could not. XE used facility plumbing and an external radiation shield. A flight engine still required flight-weight hardware, redundancy, compact packaging, and launch vibration qualification. No complete flight stage was built. A later NASA assessment placed the integrated technology around readiness level 6, a prelude to flight engine development, not a vehicle waiting for a launch date. By the end of the campaign, hot hydrogen had produced thrust through a nozzle, and reactors had reached high power and exhaust temperature. NRX A6 had run at full power for 62 minutes. XE had restarted, throttled, and operated as an integrated engine system. Those were demonstrated ground capabilities. The record did not include a flight-qualified engine or complete stage. Flight qualification still required a final core design with known life margins, repeatable manufacturing, acceptance criteria, and a full qualification campaign. The engine needed flight-weight pumps, controls, shielding, redundancy, and fault response. Those parts then had to survive launch vibration and fit within an actual vehicle. NASA Administrator James Fletcher's own continuation plan treated this as several more years of development and exploratory ground testing. The engine was only one portion of the missing flight article. A stage needed hydrogen tanks, feed lines, structure, shielding, avionics, payload interfaces, and a launch vehicle. It needed range safety rules, accident analysis, a subcritical launch configuration, a first startup policy, and an end-of-life plan. Above all, it needed a selected mission with money and a schedule. NERVA accumulated mission studies without receiving a funded operational assignment. After officials approved only an abbreviated continuation in December 1962, Rover was reoriented in January 1963 toward component evaluation and cold tests. Construction of the specific Reactor in Flight test program never materialized, although later design studies continued. Ground development survived for roughly another decade, separated from the near-term flight vehicle that Rift was supposed to provide. By the late 1960s, Mars expeditions and other large post-Apollo missions were moving farther into the calendar. NERVA kept improving, while the dates meant to justify it became less immediate. Engineers produced many candidate missions and reference designs. None became a selected, funded operational requirement that forced NASA to build the flight stage. Congressional committees sought to preserve the program for fiscal year 1972, although support was not uniform. One committee record described $58 million as a viable continuation level, $48 million for NERVA, $8 million for nuclear propulsion research and technology, and $2 million for nuclear rocket development station operations. The same record acknowledged that this funding would not begin development of a nuclear flight stage. It preserved development work while leaving the flight stage outside the funded program. On November 19, 1971, Fletcher proposed a staged continuation to Caspar Weinberger at the Office of Management and Budget. Phase 1 would fund about 5 more years of development and exploratory ground testing through 1976. A later decision would determine whether to build a flight-certified prototype. Another later decision would determine whether to fly it. The proposal was careful because the remaining commitment was large. The presidential budget for fiscal year 1973 ended the main development line. The continuation request had fallen to $25 million. NASA's budget history records the stated reasons as high annual cost and the movement of relevant mission dates farther into the future. After that decision, the demonstrated ground hardware no longer had a funded route into flight development. Nevada then wound down.
In January 1973, Area 25 Records said activity would end except for work required for safety and public welfare. Responsibility passed from the joint NASA AEC office to the Nevada Operations Office that July. By then, engine firings had ended. Management of contaminated equipment, structures, and land continued.
Decades later, nuclear thermal propulsion returned to a flight program under DRACO. DARPA and NASA planned an orbital demonstration with a reactor kept subcritical and nearly non-radioactive during handling and launch. It would start only in a predefined safe orbit. That reduced one launch hazard. It did not remove the required nuclear safety analysis, environmental review, accident planning, and launch approval.
DRACO stopped before launch. NASA TechPort records the project closing in April 2025, and DARPA issued Lockheed Martin a stop work memo dated April 2nd. In a 2025 interview, DARPA Deputy Director Rob McHenry cited falling launch costs, weaker mission assumptions, high development cost, and launch reactor risks that had been underestimated. DRACO used a different design in a different program. His explanation named several pressures also present in NERVA's history. At the Nevada test site, radiological surveys and cleanup ran from 1974 through 1983. Contaminated equipment and structures remained after the engine program ended. Demolition of the reactor maintenance, assembly, and disassembly building continued into 2010, when trucks carried away debris from a facility once used to prepare nuclear rocket hardware. The fiscal year 1973 budget ended the main development line. Radiological survey, cleanup, and later demolition continued for decades.
The poured concrete test stands still sit at Jackass Flats. Hydrogen once left reactors there hot enough to make rocket thrust. Open-air tests, failures, and destructive experiments left uranium fuel and fission product contamination that required years of survey and demolition. No NERVA engine reached space. Portions of the site remained under cleanup long after NASA left. The concrete at Jackass Flats is what a successful test program looks like when the mission disappears.